So I'm happy to introduce our next speaker, who is Ting Xue from the University of Melbourne. And she's going to talk to us about character sheaves, Hecke algebras, and Hessenberg varieties.
Thanks, Anthony. Thanks a lot for the organizers for the opportunity to speak. So this is based on joint work with Kari Vilonen and partly based on work with Tsao-Hsien, Chen, Misha, Grinberg, and we also got some combinatorics help from Dennis Stanton. So let me start with the setup of the our question. So character sheaves for graded Lie algebras. So the setup is we will think about a connected reductive algebra group over complex numbers. And now this G will have a finite order semi-simple automorphism theta on it. So the order will be denoted by M. Now this automorphism will induce a grading on the Lie algebra. So these Gi are the eigenspaces of d theta with eigenvalues some power of m through to unity. So these graded Lie algebras, they arise naturally from PID groups via Moy-Prasad filtration, and they have been classified. So there are, I guess, a few classifications, Katz by Katz and Weinberg, and then Reader, Yu, Levy, and Grossley also discussed this classification because they were motivated by representations of PID groups. So now what we are gonna consider is this group of fixed point under theta of G. Then the group K naturally acts on these graded pieces. So the invariant theory of this K action on Gi has been studied by Weinberg. So it turns out it's quite similar to the adjoint representation Gx on its Lie algebra. In the situation when M is 2, this has been studied also by Kosten-Rallis. We are in the situation of symmetric spaces and real groups. So now we write a definition. The so-called character sheaves. Now we just look at this G1 piece. All other pieces can be reduced to this situation. So we define this set of character sheaves to be simple K equivalent perverse sheaves on G1 singular support. So then by definition, this is the same as a Fourier transform of a simple K equivalent perverse sheaves on the nilpotent cone in the G-1 piece. So here we denote N the nilpotent cone of the Lie algebra, which we have seen yesterday. Now, the Fourier transform takes K equivalent perverse sheaves on G-1 to perverse sheaves on G1. Well, here we have identified the dual space of G-1 to G1 using a K equivalent bilinear form. Sorry, K invariant bilinear form. So then now what we are looking at is just the K equivalent perverse sheaves on the nilpotent cone, its image under the Fourier transform. So this here equality is because Fourier transform preserves singular support. So actually this set can be written down quite explicitly because Weinberg has shown that the K action on the nilpotent cone has finitely many orbits, the same as in the classical adjoint representation theory situation. So then now every character sheaf will be a Fourier transform of IC sheaf on the nilpotent K orbit, and with the local system that's irreducible K equivalent on the nilpotent orbit. So now we know this is actually a finite set. These are linearized analogs of Lusztig's character sheaves. so his character shifts give rise to irreducible characters of finite groups of Lie type. So now our goal is to explicitly describe this this set of character shifts. So because Fourier transform is equivalence of categories when you restrict to chronic sheaves, so every sheaf in here will be of the form IC sheaf with some support, and you know what the local system is, then we can describe all the character sheaves. So we wanted to view this as a Springer theory for graded Lie algebras. And we are hoping that it might be useful for representations of periodic groups because of the connection of graded Lie algebras with the periodic groups mentioned earlier. Any questions? Okay, so let me briefly talk about what has been done previously. So in the ungraded case, namely if we have the G action on the Lie algebra, then yesterday we seen the Springer resolution and you have the Springer correspondence, but Lusztig has generalized this to the to be able to study all the local systems on the Newton orbits. And this is somehow a theory that has led to Lusztig's character shifts. So in our current setting, we can also think about this as having a theta acting on m factors of G by permuting the factors. So then in the situation when theta is inner and G is G of n, so this is the cyclic quiver situation. Lusztig also studied all these character shifts. He has explicit description. And then in the case of so GK, this is the symmetric pair situation. So SL2 and SP2, and this has also been studied by Grinberg and Antony Lusztig. So the idea is that in these two situations, 1 and 2, so the character shifts, they are, so the local system is associated to representations of Coxeter groups. So now, again, in the situation of involution, so there has been some general study of character shifts by Ginsburg, Gronowski, and Henderson, Xihua He. But this is slightly different from our setup. Now then, again, for the involution, in some special situation, GK is SLN, SON. This is a split symmetric pair. So with Tsao-Hsien, Chen, Vilonen, we have discussed this situation. And also with Kari, for G classical groups, we were able to describe all these character shifts. So it turns out now the character shifts are associated to representations of Hecke algebras of Coxeter groups, but the parameters will be plus or minus 1. So in particular, these algebras, they are not semi-simple. Unlike here, so we were having things like a group algebra of the Val group. Okay, so now we wanted to study this general theta situation. So we follow the Euro approach of classifying character shifts. So we gave a definition. A character shift is called cuspadal if it does not appear as a direct summand of a parabolic induction of character shifts on a theta stable levy contained in a proper theta stable parabolic. So everything is theta stable here. Now, in order to determine all the character sheaves. So all we need to do is first classify cuspidal character sheaves, and then we study how to parabolic induce these cuspidals on the levies that we just described. So this is the Euro-Harshchandra approach. So because of the definition of the sheaves, so this is obvious. So then from now on, we will just concentrate on trying to find these cuspidal character sheaves. So today, for simplicity, we will just assume the groups are the classical groups, namely GLN, orthogonal group, or symplectic group. So the same technique should work with some modification for other isogenic classes and exceptional groups, and so on. So similar to the situation of Lusztig's generalized Springer correspondence. We need to take into account of central characters. So now for simplicity of statements of the conclusions, I'll assume G is a classical group. So all this I'm talking about are still work in progress, and partly they are conjectural. So we claim that there are two types of cuspidal character sheaves. So the first kind is the character sheaf themselves has nilpotent support. So these are actually quite rare, and they arise from Lusztig's classical cuspidals on G. So in particular, this says that for the situation when you think about the G act on the nilpotent cone, the cuspidal character sheaves are rare. So for example, these are studied in the Z-graded case by Lusztig. So he showed that these are, in that situation, all the cuspidals are nilpotent support. So then somehow more interesting is the full support cuspidal character sheaves. So these sheaves, they didn't appear in the classical Springer theory. So these are sheaves that has a support equal to the whole G1. And so to produce these cuspidal sheaves, so we'll make use of geometric bicycle construction. So conjecturally, these will all arise from such a construction. Any questions? Okay, so now.
So Ting, you're claiming that for cuspidal character sheaves, they're all either at one of these two extremes, they're all either supported on the nilpotent cone or they have full support.
Well, this is under the assumption that I'm in the classical groups. So for example, for SLN or a spin, and there will be other kind of support. At least for evolutions, for classical groups, this is true. Okay, so now I want to discuss this nearby cycle construction, which hopefully leads to the classification of all the full support cuspidal character sheaves. So first of all, let's recall. So first of all, not all the gradients will afford cuspidal character sheaves. So this is already the case again for ungraded situation of Lusztig's. So in that situation, if you are having an orthogonal group, then this n has to be a square, and if you have a symplectic group, then n has to be a triangular number for the cuspidal character sheaves to exist. Now, when m is equal to 2, so again, I'm having the classical groups. So then the only situation when you have these sheaves is when GK is a split symmetric pair. So for every G, there is a unique pair. Now, so then to study the general gradings, so we wanted to first look at the two special kind of gradings. One is the so-called stable gradings. These are stable in the sense of invariant theory, meaning there exists a semi-simple element whose centralizer in K is finite. So, and actually these so-called stable gradients, they have been classified again by the four people I mentioned earlier. And the second kind of gradients we wanted to look is a rank 0 gradients. Well, I haven't told you what a rank means. We will see that in a bit. But these gradients, they supposedly correspond to special prehomogeneous vector spaces. These special prehomogeneous vector spaces, they have been studied extensively by other mathematicians, supposedly related to zeta functions. And so now I'll make some vague statement about the gradings affording cuspidals. So this will be a mixture of stable grading plus these special rank 0 gradings. This can be made precise, but I won't do it here. So now I will try to get to the nearby cycles. So first of all, as I mentioned earlier, the invariant theory is similar to a joint representation. So in particular, you can find a Cartan subspace in this G1 part, so that so the key invariant functions on G1 is the same as WA invariant functions on A. So here WA is by definition NKA mod ZKA is the so-called Little group. This in general is going to be a complex reflection group. In the case of m equals to 2, this happens to be a Coxeter group, but in general, it's not anymore a Coxeter group. And these complex reflection groups, they have been classified by Shepard and Todd. So now the rank, by rank, we mean the dimension of this Cartan subspace. So all the semi-simple elements are conjugate to this Cartan subspace. So to construct this nearby cycle sheaf, we wanted to consider the adjoint quotient map. So from G1 to the categorical quotient, so which is the same as A mod WA. So now this is a little bit perhaps technical. So we wanted to take a base point in the regular semi-simple locus, and we take the fiber of this point under the adjoint quotient map. So in general, this map is, this fiber is a union of K orbits. And Grinberg has shown that it contains a unique open dense K orbit and also a unique closed K orbit. So this we denote by semi-simple. So this gives us the following diagram. So this is the open orbit and this is the closed orbit. If I take a semi-simple element here, then the fiber here will get an action of a centralizer of B in K. And this is a prehomogeneous vector space. So now we wanted to take a local system on this open orbit, which is K equivalent, but we want additional assumption so that L restrict to the prehomogeneous vector space is a rank 0 cuspidal local system. So these are the Lusztig's cuspidal local systems. So in particular, they are clean. So then we wanted to take a nearby cycle sheaf of the IC sheaf, although you could have perhaps take any extension. So this sheaf we will call it PL. Now we obtain a sheaf on the nilpotent cone. So here there might be a -1 + 1 issue if I'm working in G-1 or G1, but let me ignore that. So now Grinberg has some theorem which tells us, implies that the Fourier transform of this nearby cycle is going to be an IC sheaf, actually, supported on the whole. This is the regular locus. You take the union of all these open dense orbits. And then ML here is a local system. So turns out the rank of this local system is exactly the same as the order of the little vowel group. So, and this nearby cycle sheaf has a very large endomorphism group, so which allows us to prove things. Now I guess the point is that then you get a lot of character sheaves from this construction, namely the irreducible constituents of these IC sheaf, they are going to be character sheaves. So now I want to tell you what this ML look like. So to describe this local system here, we can reduce to the case of semi-simple rank 1. So the answer in the rank 1 situation are as follows. So this local system is roughly Cx mod Gx. So here the Hecke relation look like x minus 1 to the some power times x plus 1 to some power. So the idea of getting this local system is very interesting in some sense. So we use a D-module approach, and we need to use some B functions, but they are already previously calculated by Fumihiro Sato, so we can just use his result to derive this Hecke relation here. So then now this allows us to describe this local system M chi. So here is a theorem in progress. Suppose that the G is again classical group. Then these local systems correspond to the following equivalent fundamental group representation. So here there are some notations that I want to explain, but the upshot is that they are more or less described by a Hecke algebra associated to so here I'm writing chi. It should have been L. So let's just say that chi is some character that give you this L. So from this chi, I can get some subgroups of the little vowel group, and then so here the WA chi 0, they are also complex reflection groups. So then this Hecke algebra in our situation is associated to complex reflection groups of this form, and then the Hecke relations are for this order 2 reflections, you get x minus 1 squared is 0, and for this order m, you will get this kind of relation. So these are the Hecke algebra introduced by Breuil, Mallet, and Rouquier. And it's known that the rank is equal to the underlying complex reflection group by, I guess, Eddington wrote a proof for all groups in 2017. So now maybe I give a remark. So in the case of stable gradings that we mentioned earlier in the sense of GID theory, so this theorem was proved, but at that time we to get the rank 1 Hecke relation, we used the classification of purpose shifts in the normal crossings situation. So in the stable case, the Neoboson cone is the G1 reg is easy to describe. But in this more complicated situation, the D-module approach worked out. And then also the nearby cycle construction, this was carried out with the Grinberg and Vilonen. So this applies, we wrote in the situation of stable polar representations. So here, the polar representations were studied by Katz and Dadog. So here the stable is a little different from, it's not in the sense of invariant theory as earlier, it just means regular semi-simple orbits form a dense orbit. So which is true in our classical adjoint representation or in the situation of involutions, but it's no longer true for a general theta. So as I have mentioned earlier, so the conjecture is that all the cuspidal character shifts can be obtained from this nearby cycle shift. So here chi can change. Well, as I again also already mentioned, so this conjecture is true when M is 2. So in that situation, by looking at the nearby cycles and the parabolic induction, plus some counting combinatorics with help from Dennis Stanton, we were able to describe explicitly all the character shifts. And another remark is that this nearby cycle construction, in some sense, plays the role of the resolution. So recall that in the classical situation, we have this Untitled and the Springer resolution, and this is the Grothendieck resolution. So by pushing forward this, we obtained all the so nearby cycle is equal to the push forward of constant shift. And if you take the Fourier transform, then you obtain all the full support character shifts in this situation, where the local system is given by the group algebra, the Val group. So in that sense, so nearby cycle gives us these full support shifts, because somehow in the general theta, in the graded Lie algebra situation, we don't have a good Springer resolution that will produce all this Fourier transform of full support shifts. So now, since the combinatorics in the more general grading seems more complicated, so to prove this conjecture, maybe we can try to make use of connections with some other work. So here is a diagram that I'll try to explain. So what we wanted to understand is the cuspidal character shifts on G1. And now by Fourier transform, then we know that this is in bijection with the cuspidal sheaves on n-1, because a Fourier transform commutes with parabolic induction. So now in recent work of Lusztig and Yun, so they actually study the okay, maybe I explain that in the next slide, but so using their work, we can relate these cuspidal sheaves on the nilpotent cone to finite dimensional irreducible representations of some trigonometric dahas of Coxeter groups. And then we just explained conjecturally all these cuspidal sheaves should come from nearby cycles. And this will give us irreducible representations of Hecke algebras and complex reflection groups at roots of unity. So now we wanted to connect these two, this and this. So the idea is that there is a Kizzy functor introduced by Ginsburg, Gui, Obdam, and Rukiye, which will take some full support irreducible representations of rational dahas of the same complex reflection group here, and this will be a bijection. And then, at least in the situation of these cyclotomic complex reflection groups, there is a Kuzu duality here. First conjectured by Chuang and Miyake, and then approved by Rugi, Chen, or Vassaro. So you can relate these full support irreps of rational dahas to finite dimensional irreps of rational dahas. But now you change the dahas. This duality will give you dahas associated to Coxeter groups. And then, so finally, so Eddington has relate this finite dimensional irreps of trigonometric dahas to rational dahas. So these are, in some sense, this error here is the analog of Lusztig's from affine Hecke algebras to graded Hecke algebra. So now the idea is that, okay, I have this diagram again. So, oh, sorry, I forgot that I was gonna say something about the Lusztig-Yun construction. So maybe let me see this quickly, and then I'll summarize the diagram. So Lusztig and Yun, they study the derived category of equivalent derived category of n-1, and they describe a block decomposition. So this is based on some work of Lusztig in the Z-graded case. So let's call these blocks the Lusztig-Yun blocks. So the index set is C. So now then for each block, they have associated a trigonometric daha. What is very mysterious to me is that, so whatever these dahas, so there are some parameters and so on. So this is the same data as what Lusztig has in the classification of unipotent representation of simple PID groups. So this seems to also suggest maybe this is hopefully useful for PID groups. So then there is a theorem conjectured by Lusztig-Yun and proved by Liu. It says that the simple perverse sheaves in this block is in bijection with some simple modules with some parameters. And now to get what is in our diagram, so according to again Zhi and Qingqiang Cai, so this cuspidals in here should correspond to finite dimensionals in here. Also, this theorem was proved by Wasser in the situational principal block using a different approach. Okay, so now let's go back to our diagram. Then the conjecture is that all of these errors should be bijection. And also, so as I mentioned, so this causal duality here was established for the just the complex reflection groups GM1R. But this diagram seems to suggest some kind of causal duality for exceptional complex reflection groups. And now maybe the, okay, I don't know. Maybe Fourier transform is the same as causal duality. Well, do I still have a few minutes?
You still have 7 minutes. Could you? Can I ask a question about the diagram?
Yes.
So when you say that those arrows should be bijections, like up the top, the nearby cycle arrow. Mm-hmm. So you, I mean, having fixed your graded Lie algebra, you have some specific collection of complex reflection groups that arise from the parameters that you had before. Mm-hmm. But you don't have all of the irreducible representations of those Hecke algebras at roots of unity, do you? You also specify what the roots of unity are, and
yes,
with what multiplicities?
Yes. So yes. So that's true.
So it's not all irreducible representations of those Hecke algebras. It's some specified collection of them.
Right. The term has to be restricted to block. Sorry.
And so sorry, can you hear me now?
Yes.
So is that collection of irreducible representations what you would expect from the KZ functor if you apply it to all full support irreducible representations of those Dahas, or is it just some of them? Or?
So I expect all of them, but this diagram has to be restricted to blocks. So the representations of these irreducible Hecke representations of Hecke algebras also break into blocks, right? So I will have to everywhere restrict to the block, and it's complicated combinatorially.
Okay, but at least the blocks are parameterized by the same thing in each of the places. And
maybe I can explain this later, or
okay, sure. Yeah, no, please move on. Yeah. So you've now got 5 minutes.
Thanks. So finally, I just want to say something about the Hessenberg varieties and affne Springer fibers. So these Hessenberg varieties, they occur naturally in our setting. These are examples of Hessenberg varieties defined by Goretsky, Kotwich, and McPherson. So when they were studying some affne Springer fibers. So those affine Springer fiber admit paving by affine space bundles over these Hessenberg varieties. So in our setting, they arise, for example, in the following manner. So you can take so here K is my group of fixed point, and PK is a parabolic subgroup. And then I will take some PK stable subspace in G-1. Then I will assume that everything is nilpotent here, and then I can take its dual bundle, or sorry, orthogonal bundle. Then I will have this map to G1. So the fibers of these maps are Hessenberg varieties, but I'm particularly interested in the fibers of this right-hand side. So it turns out the fibers on the nilpotent side, these fibers are having simpler cohomology. So for example, the Springer fibers are on this side. So by Lusztig and Yun, they have proved that this cohomology has odd degree vanishing property. But on this side, in general, the fibers have a more complicated cohomology. What this Springer theory plus Fourier transform actually allow us to study this in families, right? The Hessenberg varieties. So using Fourier transform, we can transfer the study of this side to this side, if we know the explicit bijection of the Fourier transform. But okay, sorry about that. It's very vague. So, but with the Tsao-Hsien and Kari, we have studied examples of these Hessenberg varieties in the situation of the symmetric pair SL and SON. In that situation, we already see quite interesting varieties, such as the intersection of quadrics and Jacobians of hyperelliptic curves, etc. Oh, by the way, so already in Granovsky's thesis, he already sees some elliptic curves. So again, this is a for these Hessenberg varieties. So the idea is that then their cohomology is generated by irreducible representations of Hecke algebras associated with the symmetric group with the just -1 as a parameter. And then conversely, there are irreps of these Hecke algebras representations can be realized geometrically. So they will appear in some intersection cohomology of a Hessenberg variety with coefficient in a local system. Perhaps I quickly show this example that we managed to do some computation in this special case using the Springer theory. So if I denote, this is the final variety of I-planes in the smooth complete intersection 2 quadrics in the projective space of dimension 2G plus 1, then you can associate a hyperelliptic curve to this 2 quadrics. And then, so if I is G-1, this is the Jacobian of this curve. And there is also some moduli space interpretation when I is G-2. So, so we computed this cohomology of this final variety. So as a representation, it becomes this expression, and we can write down explicitly what these coefficients are. And it turns out this number is independent of G. So here, so these are built up from the irreducible representations of the Hecke algebra of S2G plus 2 at -1. So supposedly this theorem can also be generalized to graded Lie algebra setting. So finally, so in Oblomkov-Yun, they construct representations of these dahas using geometry of homogeneous affine Springer fibers. So they show that there exists some perverse filtration on the cohomology, so that this associated graded carries some action of a rational daha and a braid group. So it seems what we have done suggests that this action of braid group should factor through a Hecke algebra across unity. So now I wrote down something that might or might not make sense. So the question is motives of such affine Springer fibers. Maybe they are irreps of Hecke algebras and dahas. Okay, I'll stop there. Thank you.
Okay, thanks very much, Ting. Please join me in thanking Ting for her talk. Thank you.